In previous videos, we have talked about the stereospecificity of Diels Alder reaction, the 4+2 cycloaddition, in the sense that if we use a diene and a dienophile that is cis, we get the cis product, and if it's trans, again, this is kept, the stereochemistry of that. So in this case, when we did the product, we had the following, and cis will give you the cis. Now the reaction is also regio-specific. In English, regio is where, the place. So stereo is about the stereochemistry. So if you had the cis, you get the cis. Now the reaction is also, as I said, regio, but not specific, regioselective. So let's analyze this example. In here, we have an unsymmetrical diene, and unsymmetrical because here in this side is different that side. We have a substituent. Also in the dienophile, on one of the carbons, we have a substituent. So we have more than one way of doing this addition. We have these two possible ways. So if we do the reaction with this orientation, let's draw the product. So if I did that, my product is going to be, I'm going to do my 6-member ring as I always do. These are here my new sigma bonds. Here I will have my substituent and that. So if I have that, these are the relative to each other, the position of the two substituents. But if I now rotate this molecule and write it this way, let's see what the product will be. Now if I do that, the product will have the following form. Now I'm going to have CHO over here and the methoxy group here, farther away. So clearly we have two products. How do we decide which one is major? One of these products is major. So for that, we're going to be using resonance to understand what is how it works, the regioselectivity of the Diels Alder reaction. And again, these reactions, we have mentioned before that is favored by the electron withdrawing groups in the dienophile, but also it works very well with electron donor groups at the diene. So to be able to predict the regioselectivity, we're going to be using resonance structures. So now let's first analyze what happened with the diene here. I can have, let's see, I'm going to start with my diene. And we know that we have lone pairs here, right? That's my methoxy group. So I can draw a resonance structure like that. And I will, in this case, create this double bond here, formal positive at the oxygen and that. Of course, this resonance structure is not as significant. It contributes less to the hybrid because of having that charge separation, but the octet is complete. But what is interesting here, and that we know that the carbon here has somewhat delta negative charge, and I want to keep that in mind. So in my substrate, because we have a resonance hybrid, we're going to have, I'm going to redraw my diene, but this time I'm going to say that I have some delta negative character here. That. And that's going to be important to understand the regioselectivity of that. Now I'm going to do the resonance structure of the dienophile. And let's say that I have that. Because of the space, I want to do this. So this is what I'm doing. I'm grabbing one of those. It's the same. All we want to do is do the resonance structure. So we know that this is delocalized that way. We can do a resonance structure in which we will have now negative charge over to the oxygen. Here you have your H and positive. Again, does not contribute to the hybrid as much as the other structure, but it does explain that the structure, that hybrid, we will have some delta positive character at this carbon. But also we can do more. We can continue moving electrons, and if I do that, I'm going to do another resonance structure. And in that resonance structure, now I'm drawing it up here, since we don't have much room, but this is going to be useful. When I do that, oh, I no longer have that double bond. I have it here, but I'm going to have a positive here in this. What that means is that in the hybrid, I have some delta positive character at that carbon. So I'm going to erase that positive formal charge and just write delta positive. And I'm going to write in the hybrid, we're going to have delta negative here. And all of that, of course, is partial in the hybrid. So here, let's do the same for the hybrid. So I'm going to do partial double bond. We no longer have that partial double bond. But now if we see the hybrids of those two structure, putting together this delta negative carbon next to the delta positive carbon allows us to predict that this is better by having opposite charges close together instead of having like charges close together. So if you do the Diels Alder with this position, notice the similarity here, I have the O. So that's my delta negative end close to my delta positive end. So that will give me the major product. That's a major and that's minor. But again, we have that too, so the reaction is not regiospecific, it's regioselective. You get more of that. Again, we had explained that by using resonance structure and understanding that this carbon right here is delta negative, and this carbon right here is delta positive. So that's the best orientation in the one that is going to allow you to predict products in this reaction.